Good morning, everybody. Today we are in physics and we're talking about energy and kinetic energy and mechanical energy. So I'm going to share our class notes. So energy is something that enables us to do work. And we have had in the past, we've talked about different types of energies, and there's a lot of different types of energies. We can have chemical energy, we can have electromagnetic energy, you can have thermal energy, you can have nuclear energy. But the energy we're interested in is mechanical energy, and it's energy that's due to the position or the movement of something. And we know that energy cannot be either created or destroyed. The law of conservation tells that energy is just changing from one form to another. For example, we have stored chemical energy in gasoline. We can burn it, and that allows us to have mechanical energy to move our car. Mechanical energy has two different forms. Both of these we are familiar with: kinetic energy and potential energy, energy that is stored in a spot. Putting a rock at the top of the hill, we have that potential energy. The rock starts to roll down the hill, we now have kinetic energy, but we still have potential energy at the same time until that rock falls to the bottom or is at the very bottom of the hill. Kinetic energy depends upon speed and the mass of something. We use joules. We can see the different units there for our unit conversion. And the formula is probably something that we've all seen before. Kinetic energy is 1/2 times mass times the velocity squared. The big thing again on any of these problems is please make sure you're in the right units, that you're in kilograms, that you're in meters, and that you're in seconds, and make any of those conversions right away in your given. So I think the best thing we can do is let's just look at an example problem right away. And here we have a problem where we have a 100-kilogram linebacker and they give the speed, and I used a number that would be maybe familiar to track and field people, saying that this linebacker could run the 100 in a state qualifying time for North Dakota in 11.2 seconds. What we want to know is how much kinetic energy does he have? And then if we have a smaller linebacker or wide receiver, how fast would he have to run to have that same amount kinetic energy as that linebacker? So setting up these problems, the best thing to do and to really make it simple is the given. The setup on these problems and having variables with nomenclature on it is the key. So here I have the velocity with a small l for my linebacker, and then I have velocity of my wide receiver with a little w, just to keep track to know what do I know and what do each one of the variables mean. So the first thing I'm going to do is let's figure out the kinetic energy of the actual linebacker himself. He has the mass, we know his velocity, so figuring out the kinetic energy is rather simple and straightforward for us. Make sure you always use the square. That does seem to get lost sometimes in the problem. And we know that that linebacker now has a kinetic energy of 3.96 times 10 to the third joules. Well, we need to figure out the velocity of the wide receiver, and we know we want the kinetic energy of each of them to be equal to each other. And I do already know the velocity or the kinetic energy of the linebacker. And I know I can break down the wide receiver. I can get my mass for him and the velocity. There's a variable I'm looking for is right here, is that velocity. There's my unknown I want to solve for. So I'm going to rewrite the formula quick, solving for that velocity. Now I have the ability to just put in my variables, and then I'm going to do my math with my calculator, take the square root of it. Please do not forget to take the square root of it. So that wide receiver receiver would have to have a velocity of 12.1 meters per second. And it should be kind of an interest that for him, that wide receiver would have to be able to run the 108.2 seconds, which is faster than the world record, just to have the same kinetic energy as that linebacker. So you can see why in football, the bigger and faster you are, that's why you get drafted and make all that money. All right, so let's go to a little step farther with our kinetic energy, since this is kind of a fairly straightforward equation. Let's look at the work kinetic energy theorem. And basically what we're saying is the net work done on an object is equal to the change in the kinetic energy. So what he initially starts at and what he's at the end. What is the change in most likely the velocity, because his mass probably isn't going to change in this problem. So we're saying that the net work is equal to the change in kinetic energy. Again, keeping track of our variables and which value is for what is always a key in these problems. So today you have to do on page 166, problems 1 and 5, and on page 168, problems 2, 3, and 4. So let's look at one of our problems. Let's do page 168, number 2 together. Here I have an object that has an applied force of 1,140 newtons. It's got friction opposing that motion at 950 newtons. I know the mass of the object. I know that the initial velocity, I always want to look in these problems, did they say it started from rest? Something like that, or does it come to a stop? That's going to give me some additional information that'll help me solve the problem. Here, it started from rest. So my initial velocity is equal to 0. My final velocity is 2.0 meters per second. And I want to know how far was this object moved during this problem. I know that the equation I'm going to work is that change in my kinetic energy final minus the initial kinetic energy. And I also know work, we learned this the other day, work is really equal to force times distance. I also know that here, my initial velocity, right here, we said this is 0. So let's get rid of half of that problem right away. All of a sudden, this problem, after I substitute in that my work is equal to force times distance, I've cut away half of it right away. So now my equation is just this, and it's been simplified. And this is the net force. So really, we're talking about the applied force minus force of friction. That's what that net force is going to be. Distance, there's what I'm looking for. I know the mass. I know the final velocity. So now it's just a little bit of algebra. I rewrote my formula for distance. I've subtracted my forces, my applied minus my friction to get my net force. I didn't lose my 2 and my 1/2. It's down here now. Don't forget to square. All my units work out. And the distance that it moved is 21 meters. So you have a few more problems to do on today's homework. I will be available at any times if you need any questions. And I hope you do well. Thank you.